Hi guys, let's look at this problem set in the Mass Spec handout. We have 3 different compounds and we need to assign each compound to its mass spectrum. Okay, first thing we would want to do here, as I recommended, is to predict what type of cleavage patterns we expect. What type of ions do we expect to form? Let's look at each one of these. Alpha cleavage. Cleave to leave behind a resonance stabilized cation. This first molecule we could cleave here. That would give that carbocation. We can also show the radicals plus that radical. Of course, only the carbocations show up in the mass spec. This carbocation, we lost, what is that, 3 carbons. What is that going to be? 43. 3 carbons is 12, 24, 36. 2, 4, 7. Yes, 43. So this would be M minus 43. What is the mass? We can add this up. 1, 2, 3, 4, 5. C5. H something O. It's saturated, so this should be 2n plus 2 would be 12. Should be 12 hydrogens. 2, 4, 6, 6 on each end, yes. C5H12, saturated compound here. This is going to equal 5 times 12 is 60, 72. 72 plus 16 equals 88. So molecular weight equals 88. And if we look at the other 2 compounds, they each equal 88. So actually the fact that the mass is the same is not going to help us, because the mass specs does show an 88. But down here, this mass spectrum also shows an 88, as well as the one on the bottom, the last one. So, we're not going to be able to use 88 to help us get the answer here. We're going to have to look at cleavage. And that's typically what you're going to need to do. Okay, M minus 43, which equals what? 45. Is that right? Because mass is 88. So we expect a 45. What else could we get from alpha cleavage? Now on this side, we would have to cleave a hydrogen and leave a carbocation by cleaving a hydrogen. That's going to be a loss of 1. Typically, while that's possible, it's going to be less likely. I would look at cleaving larger groups, carbon-carbon bonds. So, mainly see loss of 45 there. Second compound. We can cleave here to give that carbocation plus a CH3 radical. This would be M minus 15, because the methyl radical is 15. And 88 minus 15 should be, what, 73? So we can predict a fragment of mass of 73 and thus a peak at 73. We could also cleave on this side of the, or between this alpha and beta carbon. And that would give, I'll draw it over here, give that cation plus the ethyl radical, and that's 29. So this is M minus 29. 88 minus 29 would be 58 plus 1, 59. Little crowded here, but for the second compound we expect or predicting a 59 and a 73. Where for the first compound we're just predicting 45. Okay, third compound. We could cleave here. That would give cation there. O methyl. That's M minus 15. Because we cleaved a methyl radical, and that's going to be just like up here, 73. We could get cation here by cleaving any one of these methyl groups. So I'm not going to repeat that. Cation on this carbon would only come from cleaving a hydrogen. We said we're not going to do that. What else could we get here? Well, this compound has a nice tertiary carbon. And if we cleaved here, we'll call it A. If we do a B cleavage here, we could get that carbocation plus an O methyl radical. Now we did cleave a CO bond. That would make that a radical if we made that a cation. The reason I'm making this carbocation is not because it's resonance stabilized like all the other ones were. See, each of the other carbocations we made are resonance stabilized. Lone pair next door, lone pair next door, lone pair next door, and we can draw resonance structure. This one is not, but it's tertiary, and so it is a good cation. And that cation is going to be, what's that, 4, 48, and 9, 57. I'm not going to do an M minus, I'll just add that one up. It should be 57. It should be C4H. 3 H's on each carbon, 9. 48 and 9 should be 57. Okay. I think it's very reasonable to predict a tertiary cation to be formed here. All right, so for each compound we have predicted masses for so-called daughter fragments, cleavage fragments. Okay, let's look at the first compound, which we predicted. Don't mix this up. I think this was just here, yeah. 45. Do we have a 45 in any of our spectra? Yes. By the way, we got to be careful. This is a textbook example. They sort of gave you peak values. I would not expect those in problems you get from me. We'd have to see that this peak is at 45 by looking right here, and then we would maybe write in that number, 45, to clarify that. We have a 45, and it's the base peak. Well, we expect 45 to be the base peak here. That's the most likely cleavage. That's why we showed it. Did we predict a 45 for the other two compounds? No, and no. Based on that, it looks like to me that the third spectrum is the first compound. If we label these as A, B, and C, I would call this compound A. Now we can always go back and change this. Let's see if the others match up here. The second compound, we predicted 59 and 73. This spectrum has a 59 and a 73. 59 is the base peak, as we might predict. 73 is less intense. Does that make sense? In both cases, we get a resonance stabilized carbocation from alpha cleavage. But in this case, we had a primary radical, where over here we just had the methyl radical, which is not even primary because it's not even bonded to one carbon. The primary radical is more stable than the methyl radical. So this route would seem to be more favorable, and indeed it looks like it was, with the 59 being more intense than the 73. But hold on, this spectrum up here also contains a 73. But it doesn't contain a 59. And if we look at the third compound, we predicted a 73 down here as well. We also predicted a 57, and the top spectrum shows a 57. Basically, this is pretty clear at this point. Top spectrum is C, the middle spectrum is B. The two peaks we predicted for the B compound are shown here. The two peaks we predicted for the C compound are shown here. The one peak we predicted for the A compound is shown here. We've also got a 56. Now, the textbook labeled this, otherwise we might not even look at it. Got to be careful, 56 is an even number, so is the molecular weight. So this is not a simple cation. If you remember the nitrogen rule, which is basically also applies here, compounds with even molecular weights, cations are going to be odd. That's not a plain cation. This is probably some type of loss of a neutral fragment, some other pathway which we may not have looked at. You may remember with carbonyl compounds we looked at and need to be aware of the McLafferty rearrangement, which eliminates a neutral molecule. But we haven't looked at anything for ethers. Okay. Basically, I'm pretty confident that I've assigned the spectra to each compound, and I began this by predicting cleavage fragments, and then I went from there. Okay. In this video, I'd also like to look at one of the worksheets in the workbook, page 38 here, which is the first problem set. Let's do these. So we have 4 compounds and 3 spectra. Not all compounds will be used. So which compound goes with the top spectrum? Well, let's sort of take inventory here. First off, do these all have the same mass? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Look like they all have the same formula. Because they're all saturated, they all have the same number of carbons. This is 1, 2, 3, 4, C6, H something O. That's going to be H14. Because it's saturated. That means 6 times 12 would be 72. 14 makes that 86. And 16 is going to make that 102. Every compound up there is 102. That's not going to help us distinguish. We need to look at cleavage. Okay, first compound. We can cleave here to give, well, cation there. Cation next to lone pair. That's a resonance stabilized cation. This is a loss of a pretty large fragment. 1, 2, 3, 4, 5. It might be easier just to add up what we have here. This is 1 carbon, 12, 16. There's 2 H's there, 3 total. 15 and 16, 31. Peak at 31. Over here we can cleave here to give, I'll come up here, that cation. But we can also cleave here to give that cation, which is M minus 15 because we just cleaved a methyl. M minus 15 should be 102 minus 15, what is that, 87? Where this is going to be, we can see what we lost. Also, if that's 31, this is an additional, it's an additional 14. It's got to be. There's a CH3, but it's 1 less H here. 14 be 45. That mass should be 45. That should be 87. So that's from that compound. You know, another way to look at this is this compound here is just this peak at 45 here. 45. Another way to look at this may actually be a little quicker here, is to say, okay, which compound do we expect a 45 from? And we already see that answer. I expect a 45 from this compound. I also expect an 87. And does this spectrum show an 87? Well, yes, it does. And so this spectrum has both peaks that we expect. I think this is compound B. Now again, we can confirm this. We can see how the other two spectra look. Now the other two spectra are a little more noisier, I would say, not as selective. We had single base peak up there. Let's see. What do I expect here? Cleave here and get boom, boom, boom. This cation, that's M minus 29 because we lost the ethyl group. That's going to be 102 minus 30 would be 72. So this is 73. But I can also cleave on the other side, and that would give cation here, and this would be M minus 43 because we lost the propyl. And that would be, minus 40 would be 62. Minus 3 more, 59. A propyl 43, is that right? 3 carbons, it would be 36. And then 2, 4, and 7, 43, yes. 73 and 59. What do we have here? The scale of this mass spec is a little different. It's more condensed, or it goes from 0 to 200, where these others go from 0 to 100. This is 72, 4, 6, 8, 80, 73. That's 73 right there. Do I have a 59? Well, yes. Right there is 59. This looks like compound C. Because compound A, I predicted 31. Now there is a 31 here. But it's not the base peak. The base peak is 59. Which compound up here do we more strongly predict a 59? Well, it's this one here. We predicted a 59 for it. Okay, compound D. We could cleave here, and that would give that cation. That's M minus 15. That equals, we did that before, yeah? Up top, 87. We could cleave on the other side. Hold on, this looks just like compound B, because that would be a 45. We also predicted that for compound B. We labeled here compound B. (8745) coming from these two cleavages. Again, we predicted the same molecular weight ions for B. Okay. That makes me wonder if this is actually compound B here, or if maybe this is compound D. How are we going to tell the difference between these two? Well, one thing I see is that this compound, we could also form a tertiary cation. Cleavage at the same spot, but what if it left the cation there and the other carbon was a radical? In this case, that would not show up, but this one would, and that compound is or that fragment, that ion, is, we saw that on the previous page, that's the tert-butyl carbocation, that's 57. 48.9, 57. The difference between B and D is, D we also expect a 57, but we do not expect a 57 for B. Now this mass spec 55 shows a 57, but it's very weak. Let's look below. The base peak is 57. Base peak. That gives us our answer right there. We predicted a 57 for D. We also predicted 87 and 45. Does it contain those fragments? 85, 6, let's see, 89, 88, 87. It also contains 87, which we predicted. Does it contain the 45? Yes, it contains the 45. Just like the first spectrum contained the 87 and 45 for B. The difference being The third spectrum, spectrum, also contains the 57, which we see could come from the forming the tertiary cation. BCD, does that mean that A is not assigned? A, we predicted 31. There's essentially no 31 down in the last spectrum. There is a 31 in the second spectrum, but again, it's not the base peak. We want to sort of make sure that we're predicting a 59, and indeed we do with compound C. And then the first spectrum, 31 is quite small. So I'm pretty confident that we have B, C, and D assigned, and compound A is sort of the fourth one that is not assigned. Okay. So there's some practice. Work through that for the first problem set, and so there's a couple of other problem sets for you to work, including a couple that have IR included. And on these, page 41, it's just one compound. Which compound belongs to these two spectra? And I'm providing an IR of the compound and a mass spec of the compound. So these can be complementary. Also gives you a chance to review and remember your IR. And we can make use of this. Page 41. Actually, I'll go ahead and work one of these because there's another one, I believe, on page 42 for you to work. So I'll go ahead and look at this here. What do we have? 3,000? Remember the magical line of 3,000? We have sp3ch. I would hope so, because every one of those compounds has sp3ch. No carbonyl. About 1700 range. I mean, this is not a carbonyl. The carbonyl would be a strong peak. No carbonyl there. Guess what? We can already exclude those two compounds. I see an alcohol here. I don't see an alcohol in the IR. That's too weak. That might be a little water, but that is certainly not an alcohol. Certainly not a textbook alcohol. No alcohol. I'm thinking we can exclude that there. The remainder are ethers. It's reasonable. This IR could match any one of these remaining ethers, yes. sp3ch. The rest is just fingerprint peaks. Ultimately, from that point, it just boils down to which ether is it. We're going to have to look at the mass spec to determine that. Let's see. These 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. These have different formulas. This is C6H something O. Saturated, so this is 14. 1, 2, 3, 4, 5. This is C5 something O. This is 12. This one here, 1, 2, 3, 4, 5. This is also C5H12O. Those have the same mass. What's the mass of this? 6 times 12 would be 72. 72 and 14 would be 86. 86 plus 16 equals 102. That was the same as over here, right? Yes. This is going to be 5 times 12, 60. 72 and 16, 88. Since we have a different in mass, we could use the mass spec molecular ion if one is present. M plus equals, I do see an 88. Now it's quite small. I certainly don't see a 102. We have to be careful though. Whoever generated this, now if there was a peak there, I assume it would be shown. If there's not a peak there, it could be that it's just not shown and the molecular ion was just not present. Seems though that the molecular weight may be 88. Thus we may be excluding this one here. Let's look at here. We got a peak at 59. The mass is 88. This is M minus 29, which is loss of an ethyl group, ethyl radical. Between these two here, which is most likely to lose an ethyl? It would be this one. We can cleave here to get that carbocation, resonance stabilized. This would be M minus 29, and that would equal 59. Here I expect to lose a propyl group, not an ethyl. Looks like to me the answer is F. What is my evidence? Well, there's no carbonyl, so we've excluded these. There's no OH, so we excluded that one. The IR could match any one of these last three ethers. But the mass spec seems to show a molecular weight of 88, or support that. It does not seem to show a mass of 102. Again, that was cut off, but that sort of tells us that maybe it wasn't there. In terms of just approaching this textbook example here. In real life, you may have the entire spectrum to look at. The base peak is 59. Which compound up here do I expect a cleavage to give 59? The one on the end? Not that one. Nor this one, because this one I would expect to lose 15 or 43. Where this one I expect to lose 29. Interesting though, if this is 43, that would be 36, yes, 36, 2, 4, and 7, 43. 102 minus 43 equals 59. We have a peak at 59. That does lead to a little wondering if perhaps could it be compound D and the molecular ion is not showing up. We were not even shown that for some reason. But if you cleave from the molecular ion, we can get 59. There's a chance that that could be the case. Certainly I think we've excluded this one because loss of 43 would not give 59. It would give like 45. But again, I'm going with F because I'm assuming that the molecular ion would have been shown. We also have an 88 here. The 88 would be the molecular ion. This compound you would not expect at 88, although it is quite small. Okay, I went on with that for a little bit. Ultimately, though, it boils down to we can exclude these three pretty quickly. The only one up there that you would expect a 59 from, well, that's not quite right. 88 and a 59. Okay, give this last one a try. Oh, this last one. This last one, there's no choices given. We need to determine the structure from scratch. Not a match, but come up with a structure, complete structure on our own. That's okay. Very doable. We have an IR, which gives us some structural components, functional groups. We have a mass spec, which could give us the mass of the compound. Give that one a try, guys. Okay, so this was a couple of worked examples for the mass spec. I hope it was useful.